The mixing process is perhaps one of the most important unit operations within the chemical process industry. This operation refers to the manipulation of a heterogeneous physical system with the intention of making it more homogeneous through a mechanical forcing of the fluids involved in the mixture. The geometry of the agitation tanks significantly influence mixing patterns. However, the impeller has been shown to be the most important factor in defining the hydrodynamics of the stirrer system. Thus, the agitators are divided into those that generate axial flow lines and others that cause radial flow currents. For the latter, the Rushton turbine is the most widely used, and that is why in this project an agitation mobile is designed and then evaluated by CFD, analyzing the influence of the shear rate and viscosity on the process's mixing.
On the first part of this project, the Russian mixer geometry was used to perform simulation with the program STAR CCM+, at different rotation rates to determine the agitator power curve. On the second part, a new mixer was designed keeping the same dimensions of the tank and the same dimensions of the agitator to improve the power of the previous Russian mixer. For our agitated tank, only the shape of the impeller was changed. This responded to a revision in literature that assured better NP results for such shape.
The new impeller design was based on a radial flow impeller in which the impeller blades are similar to the Russian impeller but with a significant curvature. This impeller is called black swept with disc and it has a fan-shaped impeller assembled with annual secture-shaped concave blades. Some studies have shown that this type of impeller causes a reduction of the power number by 26%, and also an increase in the residence time of vortex at the impeller tip, which results in stronger and smaller vortices at this region. The space between the lower and upper vortices presents the location of high turbulent kinetic energy. Surface remeasure, polyhedral measure, and Prim's layer thickness were used in order to create the mesh for both stir tanks. The specifications for the mesh were said to be the ones given by the project. The polyhedral mesh, as its name implies, generates polyhedral cells. This kind of mesh was chosen because their cells are superior to tetrahedral cells due to their large amounts of phases. In consequence, polyhedral cells have lower skewness, which improves the accuracy in calculations and creates a more homogeneous mesh. Moreover, polyhedral mesh, compared to a tetrahedral mesh, requires 5 times less cells to reach the same level of accuracy, resulting in a fewer time of calculation. For this project, the shown physical models were used to correctly simulate both stir tanks in the program STAR CCM+. These models are all-white plus wall treatment, implicit unsteady, SST kappa omega, cell quality reanimation, kappa omega turbulence, three-dimensional, constant density, liquid, transition boundary distance, exact wall distance, RANS, turbulence suppression, gradients, segregated flow, and turbulent. For the given Russian turbine, a total number of 79,370 cells was found. The cell quality was good, with most of the values being above 0.6. Additionally, worldwide plus presented some large values that were expected to be obtained due to the turbulence of the model. Our agitated tank presented 757,511 cells, as well as the Russian turbine. This tank presented an acceptable cell quality found mostly above 0.6. The results for worldwide plus presented values between 0 and 1 that were not expected because the model was not better than Russian and no turbulence appears to be happening.
Some of the values of power number we obtained with the simulation and CFD for the Russian turbine differ in a large percentage for the theoretical values. It is evident that the percentage of error increases as the Reynolds number decreases, meaning that the Russian turbine doesn't simulate laminar regimes very well, but it is very acceptable when it comes to transition and turbulent behaviors of the fluids. Studies show that on Russian turbines there are different correlations to calculate the number of power depending on the fluid's regimes, which means that the number power has a different relation with the Reynolds number as it varies.
On the other hand, the shear rate and shear stress are one important factor to analyze in turbines because high shear rates can break the membrane cells of possible microorganisms studied and affect directly the missing procedure. On the results obtained for the Russian turbine and the new impeller design, it was evident that the shear rate increases as the Reynolds number did as well. These results show a clear relation between the angular velocity n and the shear rate, which also depends on the flow regime of the fluid. Also, it was evident that the relationship between the shear rate and the power is as it is shown in this equation. Most importantly, it was noted that a larger shear rate presented the need of a bigger amount of power delivered to the system. In our case, the Russian turbine presents a requirement of power that is almost 5 times the one required by our tank. Additionally, most of the reports for the lowest values of Reynolds in our tank tended to present negative power number, which led to a disposal of said values since they weren't of any use, as you can see in the table. While the Russian tank reports efficiency lower than 5%, our tank presents values that are between 9% and 22%. This indicates a close relation between the hydraulic power and the system power that implies that much little amounts of energy are being lost to their surroundings. The power and efficiency aspects might be good since they would indicate that the proposed model can be better in terms of rentability and energy consumption. If it wasn't for the fact that all the values for the new model are extremely low, which could indicate hardly any movement is being detected. This aspect can be better appreciated in the comparison of the streamlines of both fluids, which tend to look as if there was a difficulty associated with trying to move the fluid in our model.
This situation can also be noted in these scenes of vector velocity. While the Russian turbine is able to provide higher levels of velocity to the entire fluid, our agitated tank is only able to steer the parts of the fluid that are much closer to the impeller, meaning that less energy is being transmitted to the fluid from the impeller. Moreover, it can be noted that our model presents issues in the axis part, where some fluid is being leaked, which could present important losses in the power number results. A problem that may have influenced the skewed results on our device might have to do with the fact that the coordinates that were brought from inventor were not placed in the origin and had to be adjusted directly on StarCCM+, deriving impossible inconsistencies in the generation of reports that may have not been noticed. On the other hand, there was the pending risk that this model might reduce the power numbers up to 33% of their initial values, but our results show diminutions as big as 98%, which is a very unacceptable and unreliable measurement. Perhaps a better design might have been achieved by adding more blades, since a larger amount of contacts might indicate a larger need for power and consequently larger power numbers. The use of more viscous fluids would result in values of Reynolds numbers that are less than the ones studied in this project. Consequently, the power numbers would decrease. In fact, according to the study literature, power number values would present its greatest decrease in the laminar zone, whereas it would maintain a constant behavior for turbulent regions, independent from the rotational speed applied.